Welcome back. In the last video, we left off on this slide where we saw how acetylcholine is synthesized from choline and acetyl coenzyme A via chat, how it's put into vesicles, which then go to the synaptic cleft. Acetylcholine's released into the cleft, where it can then bind to receptors on the postsynaptic cell. Acetylcholine esterase then enters the synaptic cleft and breaks down acetylcholine into choline and acetate. This is then reuptaked into the presynaptic cell, where choline can then be used to synthesize even more acetylcholine. Now, acetylcholine is synthesized in that presynaptic cell, but the synthesis of acetylcholine is tightly regulated. So there's three things that can input how much acetylcholine is synthesized. The first would be product inhibition. In other words, the levels of acetylcholine in the cell actually inhibits the synthesis of more acetylcholine by chat. So acetylcholine itself kind of inhibits chat, therefore not allowing chat to synthesize even more acetylcholine. So think of it kind of more as a competitive antagonist, where it's not just the first acetylcholine made isn't going to block chat, but once you have a lot of acetylcholine, there's going to be too much happening, which will then prevent chat from synthesizing more acetylcholine. The second thing that will regulate the amount of synthesis of acetylcholine would be the precursor availability. In other words, how much choline and acetyl coenzyme A there is available to be synthesized into acetylcholine. So of course the first big thing would be the amount of dietary choline that someone has. Now, it has been looked at to increase the dietary choline in people in order to allow for more synthesis of acetylcholine, so that we can use it as a treatment for conditions where the cholinergic system is damaged. A great example of a damaged acetylcholine system would be in Alzheimer's patients, where you see that decline in cognitive function and memory. However, some of the work around increasing the dietary supplementation of choline has actually failed for two reasons. The first is that increasing the amount of dietary choline in Alzheimer's patients actually failed to improve symptoms. So just increasing the choline that an Alzheimer's patient has did not lead to improved symptoms, possibly because of we already had too much acetylcholine happening, so increasing the acetylcholine just wasn't available. But also, there was this kind of, I think it's kind of funny, a little sad side effect, that in the periphery, choline is metabolized into trimethylamine, which is a compound that gives off a very fishy odor. So people that took these dietary supplementation of choline actually started smelling like fish. Not very pleasant. And, we didn't have the improved symptoms and cognitive functions to kind of outweigh your new fishy smell. So it's not recommended anymore. They've kind of stopped trying to use this dietary supplementation of choline as a treatment for these patients with these conditions. So just some fun facts about that. And then the third thing that can limit or regulate the amount of acetylcholine that's synthesized would be your neuron activity. So increased activity of the neuron will lead to increased synthesis of acetylcholine. obviously to make sure that there's sufficient acetylcholine available during these periods of high activity. So it's kind of that use it or lose it mentality. If you're not using the neuron as much, you're not going to have as much synthesis of acetylcholine because you just don't need it. But if you use the neuron more, you're going to get more synthesis. Now, once it's made, how is acetylcholine stored and then released? So as I mentioned in that figure a few slides ago, acetylcholine is stored in vesicles at the nerve terminal. And this is stored by the molecule vesicular acetylcholine transporter. Very straightforward name. Should, if you gotta guess the name, just go with what it sounds like it does. Now these transporters can be inhibited as well. So there's the drug vesimicol that actually inhibits the transport of acetylcholine to the synapse. So what it does is it pretty much causes the acetylcholine to get stuck in the presynaptic cell so that it cannot be released into the synapse. And by blocking the vesicle transport, this actually depletes the pool of release-ready vesicles. So we actually will see a decrease of synthesis as well, because now we don't have anywhere to store the synthesized acetylcholine. Acetylcholine will be released by the classical vesicular exocytosis. So it gets synthesized, stored in these vesicles. The vesicular acetylcholine transporter brings it to the cell membrane at the synaptic cleft, and then we've got this exocytosis via a voltage-dependent calcium influx. So with an influx of calcium at the cell membrane, then it allows the vesicle to fuse with the cell membrane and release the acetylcholine into the synapse. Now, we can also apply certain drugs that actually trigger the release or the exocytosis of acetylcholine without this calcium influx. So the most common would be latrotoxin. So this is more commonly known as black widow venom, and this only works in the peripheral nervous system. So that's why black widow venom acts on it can cause like paralysis, it can cause muscle pain, tremors, nausea, and excessive sweating. So these are all symptoms in the peripheral nervous system, not the central nervous system. And because the reason it only acts on the peripheral nervous system is just because latrotoxins are very large molecules, so they're too big to pass through the blood-brain barrier. And so what it does is it triggers the neurotransmitter release of acetylcholine by actually kind of breaking through the membrane of the target cells and kind of creating new calcium channels so that more calcium can flood into the cell without having to be activated via an action potential. So we get this subsequent calcium influx, which then triggers the release of the vesicles without an action potential. So now what about the reuptake of acetylcholine? So remember, acetylcholine is broken down in the synapse into choline and acetate. So the breakdown product choline is then transported by the choline transporter back into the presynaptic cell. Now, the majority of this choline is then recycled to make even more acetylcholine, but not all of it is. Some of it will be removed from the body, and that's why you have to keep eating foods that contain choline. Now, we can block the reuptake of the choline by using the drug hemcholine 3. And what this does is it leads to the synaptic accumulation of choline and a rundown of activity. In other words, the choline gets stuck in the synapse, so it can't get back into the cell. It can't go on to form more acetylcholine, so therefore the synthesis of acetylcholine slows down. The release of acetylcholine gets slowed down, so you pretty much turn off kind of the whole system. Everything gets backed up in the synapse, and all the acetylcholine turns into choline, and nothing can really happen anymore. Now, a common drug that you guys have probably heard of that actually works at this site would be Botox. So Botox is a neurotoxin isolated from the bacteria Clostridium botulinum. So clostridial neurotoxins are the group of neurotoxins from this bacteria that causes paralytic effects of botulism poisoning. Okay, so what it does is that our botulinum toxin will prevent the vesicle binding to the cell. So what it does is it prevents acetylcholine from leaving the presynaptic cell. Okay, so if you were to inject botulinum toxin into this area, so like say someone that's getting like face Botox or something, what they're doing is they're injecting the botulinum toxin pretty much right here, right by the muscles and where the neurons connect. And what it does is it paralyzes the neurons that talk to the muscles because the acetylcholine cannot be released, so the muscles then do not know to contract. So the muscles will stay relaxed. Okay, the muscles can't contract because there's no acetylcholine telling it to. Now, we do use Botox for therapeutic effects, not just for cosmetic effects. It can be used for treatment of people for cross-eyedness. You can apply Botox and it causes the muscles in your eye area to relax, and so you don't get the cross-eyed. It can relieve eyelid spasms, facial spasms, again by preventing the muscles from being able to contract. It's also great for treating migraines. Now, there are some other drugs that act on acetylcholine. One of the biggest group of drugs are actually insecticides. And insecticides, a lot of them act on neurotransmitters of acetylcholine because in insects, then they don't really have that blood-brain barrier, and so acetylcholine works not just in the peripheral nervous system, but also the central nervous system. So if we block the effects of acetylcholine in insects, then we're actually able to affect the central nervous system as well. So the big group would be plant alkaloids. These are secondary metabolites, which are commonly synthesized for defense against insects or animal predation. So a lot of plants will produce these plant alkaloids. Now, we can actually kind of exploit the effects of these plant alkaloids for commercial and therapeutic benefits. So we can actually take some of these molecule substances that we found by studying these plant alkaloids to make drugs that affect acetylcholine breakdown. So, for instance, we've got some acetylcholine esterase inhibition drugs, and what that does is it prolongs the availability of acetylcholine signaling in the synapse. So by allowing acetylcholine to be in the synapse longer, we're allowing it to bind to the postsynaptic cell receptors longer, hopefully increasing the effects of it. Okay, so that's why you might use an acetylcholine esterase inhibition drug. One such drug would be a plant-derived toxin called physostigmine. Now, this is a blood-brain barrier permeable inhibitor of acetylcholine esterase. So in other words, this is a toxin made in drugs that's able to actually cross the blood-brain barrier, so it can affect human brains to inhibit acetylcholine esterase. So it prevents the breakdown of acetylcholine. Now, this toxin is found in calabar beans. And what this does is it can actually lead to poisoning, where you will see slurred speech, confusion, hallucinations, convulsions, coma, and even death. Now, there's a fun, well, not really fun, but there's a story around calabar beans where we kind of figured out how this works, or why we even studied it in the first place. And that's because in the 19th century in West Africa, then it was reported that some jails would use calabar beans to determine a prisoner's guilt. So what they would do is that if someone was suspected of being guilty of something, they would force them to eat calabar beans, and they thought, well, if someone's not guilty, then they will either throw up the beans, or they'll just walk away unaffected. However, if they're guilty, then you're going to get some of these effects. So obviously, since this is a poison, it's a toxin, not many people were able to beat it. So a lot of people were found guilty, even if they weren't, because of the effects of the calabar bean, because they were being poisoned and expected to somehow, function normally to prove their innocence. So that's kind of the story behind calabar beans. Now, obviously, we won't freely give people this toxin because it's not good. But there are some synthetic analogs of this toxin that are impermeable to the blood-brain barrier. In other words, it's another toxin that causes acetylcholine esterase inhibition, but it's not able to cross the blood-brain barrier, so we're only going to see the effects on the peripheral nervous system. So two of these drugs would be neostigmine and pyridostigmine. And these are actually used to treat some autoimmune diseases, such as myasthenia gravis, MG. Okay, so you can also just call this MG. Okay. And so, because these only act on the peripheral nervous system and not the central nervous system, you don't get these negative effects of coma, death, hallucinations, that kind of thing. You'll only get the effects on the muscles. Now, all of these toxins are reversible inhibitors. In other words, they don't bind and stick to it forever. they do eventually remove themselves from acetylcholine esterase. So you would have to have repeated administration of these drugs to see effects. And that's why people that eat calabar beans can survive, because if they don't eat enough, then they'll just have some of these lesser symptoms, and then they'll get over it, because the toxin will remove itself and be flushed from the body. Now let's talk about a little bit about some of these this autoimmune disease that we use acetylcholine esterase inhibitors to treat. So this would be that MG we just talked about, the myasthenia gravis, and this results from a immune response to acetylcholine receptors at the neuromuscular junction. So by treating patients with these drugs that inhibit the acetylcholine esterase, then we're able to prolong the amount of acetylcholine in the synapse. And so what this image is showing is kind of how MG affects this neuromuscular junction. So in normal people, normal neuromuscular function, then we've got the presynaptic cell that releases acetylcholine. We've got the acetylcholine receptors on the muscle cell where acetylcholine can then go bind. And now remember, acetylcholine esterase will then be released and break down the acetylcholine in the synapse. Now in a MG patient, then at the neuromuscular junction, what happens is, because it's an autoimmune disease, then we actually get antibodies from our own body are released, and they bind to these acetylcholine receptors on the muscle cell, preventing acetylcholine from binding. So that means we have less receptors available for the acetylcholine to act upon. And this is why allowing there to be acetylcholine in the synapse a longer time, preventing the breakdown of acetylcholine, helps these patients, because it allows more entry, more activation of these receptors. Now, if you don't treat this, then what we see is that patients with MG have fluctuating muscle weakness and fatigue, again, because their muscles aren't able to activate normally. Now, there are some irreversible acetylcholine esterase inhibitors. So these would be inhibitors that bind permanently, and in order to get rid of them or to relieve symptoms of these inhibitors, we actually have to wait for the acetylcholine esterase to be removed from the body and new ones to be made, and that can take some time. So these are a lot, they tend to have more negative long-term effects. And again, we see this in some pesticides. So in organophosphate pesticides, so the biggest example here would be malathion, then these pesticides will bind irreversibly. So we see that while it was first designed to be a pesticide, so it does affect humans a lot more, insects a lot more, we do see that there is some human toxicity as well after long-term exposure. So what's happened is that a lot of places, including the majority or all of Canada, has actually banned the use of these pesticides. The last holdout was Winnipeg, in case you were wondering. They finally got rid of the use of it in 2017, in case you were wondering. So not just pesticides have act as irreversible acetylcholine esterase inhibitors, There's also nerve gases, so sarin and VX are also irreversible inhibitors. So these are two nerve gases that have been used in some wars or in some attacks, terrorist attacks, domestic attacks, and have some very serious effects. So sarin was infamously used in the Tokyo subway attacks of '95. I'm sure most of you aren't old enough to remember that. And then there was risk of exposure to both sarin and VX in the Gulf and Iraq wars. Now, there are some kind of preventative agents. Pridostigmine, which we talked about before, has been prescribed as a preventative agent for this nerve gas poisoning. So soldiers would actually take pyridostigmine preemptively. Pretty much every day they would take it, so that if they were to be exposed to sarin or VX, it would actually block the effects, because they actually compete for the same site. So if you have pyridostigmine already in your system, then sarin and VX cannot affect you. So this is just a fun graph kind of showing the effects of pyridostigmine in rats. So in this example, then mice were subjected to a forced swim test. So the forced swim test is a common test to evaluate stress and the effectiveness of antidepressants. And what we saw is that, pyridostigmine is not supposed to be able to permeate the blood-brain barrier very well. We actually see that under a stressful condition, such as the forced swim test, or in humans like the Gulf War, then we actually see increased permeability of the drug. What we see is that the amount of acetylcholine esterase compared to controls, then in unstressed, then we still have a good amount of acetylcholine esterase activity. However, in a stressful environment, then we have a decrease in acetylcholine esterase activity due to the permeability of the blood-brain barrier, which allows the pyridostigmine to enter the brain and cause a decrease in activity. So this is what's thought to be one reason for the Gulf War syndrome. So here then you see confusion, ataxia syndrome, so cognitive impairments, dizziness, balance and coordination problems in patients of the Gulf War syndrome. Now, again, this is just a theory of what causes it, but there are many trials that found in humans that this wasn't the reason behind it. So we can't say for sure that the stress of the war and the soldiers' daily intake of pyridostigmine led to the Gulf War syndrome. So that's it for today's lecture.